Welcome to the 15th lecture of module 4. In this module, we are discussing reactor design. Before going to this lecture, let us briefly discuss what we have covered in the last lecture. In the last lecture, we have covered optimum temperature progression in a batch reactor. So, we have seen for 3 different cases how to obtain the optimum temperature. We have seen for a case of irreversible single reaction, the maximum allowable temperature is the optimum temperature. Even in case of the reversible endothermic reaction, the maximum allowable temperature is also the optimum temperature. The only case which we have considered where we can find the optimum temperature if we wanted to run at a single temperature, that is for single exothermic reversible reaction, where the change in temperature changes the equilibrium conversion. And we have seen how to go about to design the reactor following a temperature trajectories instead of a single temperature. So, we have considered exothermic reversible first order reaction and we have considered the cases. Now, in this module we will consider mass and energy balance in plug flow as well as mixed flow reactors. The lecture outline are as follows. So, we will consider total mass balance in plug flow reactor, then we will consider material balance in plug flow reactor, and particularly energy balance is our interest when we look for temperature and pressure effects. So, energy balance in PFR, then optimum temperature progression in PFR, then we will consider similar mass and energy balance in mixed flow reactor or CSTR. So, let us start with the species mole balance for constant density plug flow reactor. In this case, we assume that the velocity in the axial direction only through the tube. So, we consider the plug flow reactor is as a tube and the velocity is only in the axial direction. We also assume that the velocity and all other quantities are constant across the tube diameter and diffusion and conduction in the axial direction are negligible. So, there is negligible diffusion in the axial direction and the conduction in the axial direction. So, if we consider that, with this assumption we can write the species mole balance as T dx, velocity is Vx in the axial direction and Ck is the concentration of any species K would be equal to, for m number of chemical reactions we can write summation over I is equal to 1 to m alpha I m I k r I. Now, if the velocity is independent with the axial direction, that is for constant density, then so Vx is independent in the axial direction. So, we can take out V x from the differential equations from the derivative. So, we can write V x d c k dx would be equal to summation over I is equal to 1 to m alpha I k r I. Now, if we define the residence time, that is, so defining residence time tau is equal to x by V x. X is the length of the tube divided by V x is the residence time tau. So, then we can differentiate d tau would be dx by V x. Now, if we substitute, we have these equations of species mole balance V x d c k dx is equal to summation over I is equal to 1 to m alpha I k r I. Now, if we substitute these things dx by V x, this would be d c k d tau would be equal to summation over I is equal to 1 to m alpha I k r I. So, this is the species mole balance equation for constant density flux flow reactor, and this is identical with the constant volume batch reactor. Only the reaction time in case of batch reactor T is replaced with the residence time tau. Now, if the density in the reactor cannot be assumed to be constant because of the changes in number of moles or in the changes in the temperature of the gas, then the plug flow reactor balance are not identical with that of the batch reactor. So, for variable density system, the species mole balance equations between the plug flow reactor and the batch reactor, they are not identical. But in this case, still we can define the residence time in a similar way, like we can write tau is equal to V by V x naught. So, V x naught here is the axial velocity at the inlet, then these equations, that is d dx of V x c k is equal to summation over I is equal to 1 to m alpha I k r I. This can be written as, with substitution of this tau, would be d d tau Vx by Vx naught Ck summation would be equal to summation over I is equal to 1 to m alpha I k R I. So, this is for variable density system in a plug flow reactor. This is the species mole balance equation. Now, the total mass balance can be written as the velocity at a given point in the reactor can be related to the density at that point using the total mass balance. So, for steady state plug flow reactor, the mass balance reduces to d dx rho Vx is equal to 0. That means, if we integrate with the initial conditions, at t equal to 0, Vx is equal to Vx naught and rho is equal to rho naught. So, if we integrate this, we will get rho Vx would be equal to rho naught Vx naught. So, this is the total mass balance equation. Now, for the plug flow reactor, now the local velocity. So, we have rho Vx is equal to rho naught Vx naught. Now, the local velocity can be computed using the ideal gas law using local composition and temperature. So, if we use the local composition and temperature, we can calculate the local velocity. So, like for ideal mixture, the velocity we can write Vx would be equal to rho naught by rho into V x naught from this relation. So, then we can substitute n by n naught, t by t naught and into p naught by p V x naught. T is the temperature, n by n naught is the ratio of the number of moles at a particular position to the number of moles in the feed, and P is the pressure. Now, the most direct measure for the reactor capability to carry out the reaction can be obtained using the local residence time based in the inlet conditions or the inlet flow rate and the reactor volume. So, we can write tau is equal to L by V x naught, which is equal to V by Q naught. So, Q naught is the volumetric flow rate of the reactant to the reactor. V is the volume of the reactor and L is the length of the reactor. Now, we can write the corresponding energy balance equation for the ideal PFR as rho naught Cp cap Vx naught dt by dx is equal to summation over I is equal to 1 to m minus delta H I R I minus 2 u by R t into T minus T c. So, here R t is the tube radius, U is the overall heat transfer coefficient, to the for the heat transfer through the tube wall. So, this heat transfer is through the tube wall to a heat exchange fluid maintained at temperature T c. So, this heat flux could take many other form depending on the heat transfer area and the tube diameter and all. So, the other terms are the typical density, heat capacity and velocity we have defined earlier. If we introduce here the residence time, then we can write this relation as, so introducing residence time and dividing through by the density and specific heat. So, we can obtain dt d tau would be equal to summation over I is equal to 1 to m minus delta H I by rho naught Cp cap R I minus twice u divided by R t rho naught Cp cap T minus T c. So, this is the basic energy balance equation. This is basic energy balance equation for the flux flow reactor. So, this is almost identical with the energy balance equation of the batch reactor, the only difference is the form of the heat transfer through the wall, and this is valid for non constant density and constant density as well. But if we consider adiabatic plug flow reactor, for an adiabatic plug flow reactor with a single overall reaction, there is a simple relationship between the reactor temperature and the reactant concentration, just we have done for the batch reactor. Equations for a single reaction in an adiabatic constant density PFR in terms of the concentration and production rate of the reactant A, we can write dCA d tau is equal to minus Ra, and energy balance equation should be reduced to rho Cp cap by minus delta H dt by d tau, which is equal to Ra. So, from these two relation we can equate the rate of chemical reactions, and we can write rho Cp cap by minus delta H dt d tau would be equal to minus dCA d tau, and if we integrate, we can obtain a simple relationship between temperature and concentration. So, T minus T naught would be equal to minus delta H by rho Cp cap into Ca naught minus Ca. So, this is the relation as we have obtained for the batch reactor. Same relations we can obtain here between the temperature and the concentration for a single reaction. Thus, the adiabatic reaction temperature that we defined in the batch reactor has the same definition and value in case of the plug flow reactor. So, we are not introducing that part over here on the adiabatic reaction temperature. Now, the optimum temperature progression. In case of batch reactor, we have discussed how the temperature, optimum temperature progression would change. It is similar to the batch reactor temperature progression phenomena. So, obtaining the optimum single temperature or temperature profile in a PFR is also very similar what we have found for the batch reactor. If we plan to operate the reactor isothermally at a single temperature, then there may be an optimum temperature to select. For a single irreversible reaction, in this case the optimal temperature is simply the highest possible temperature, since that will provide the highest possible rate. This temperature, how we can determine? It will be determined by the boiling of the reactants or the operational limits of the reactor, that will tell what is the maximum permissible limit for the reaction to maintain. Now, for a single reversible endothermic reaction, the optimum temperature is also simply the highest possible temperature, since that will provide the highest possible rate, and that will be determined again under the same conditions of boiling of the reactants or operational limits of the reactor. The only case where there may be an optimum temperature for a single reaction is when we have an exothermic reversible reaction. So, for an exothermic reversible reaction, we can have optimum single temperature or a temperature progression. For such a reaction, the rate will increase with temperature, but the equilibrium conversion will decrease with increasing temperature. As in batch reactor, the optimal temperature profile for a single reaction is the one that optimizes the reaction rate at every point in the reactor. The discussion of the batch reactor has been slightly modified and discussed over here. So, let us consider single first order reversible reaction. So, we can write a rate R is equal to K1 into Ca minus 1 by capital K Cb. So, A to B reversible reaction. So, we can use the Arrhenius relations of the rate constant and the equilibrium constant as A exponential minus E A by R T into C A minus A by K naught exponential minus E A minus delta H divided by R T into C B. Now, if we take the partial derivative with respect to temperature at a fixed concentration, then we can write. So, taking partial derivative of this with respect to temperature at fixed concentration. So, we can write del R del T would be equal to A E A by R T square exponential minus E A by R T into C A. So, we can write minus A into E A minus delta H divided by K naught R T square exponential minus E A minus delta H divided by R T into C B. So, this is the partial derivative, and now if we set this equal to 0 and dividing both sides with R T square by A, we can write del R del T is equal to 0 or multiplying through R T square by A. We can obtain E A exponential minus E A by R T optimum into C A would be equal to E A minus delta H by K naught exponential minus E A minus delta H divided by R T optimum into C B. Now, if we rearrange this, we can write E A minus delta H by K naught E A C B by C A would be equal to exponential minus delta H by R T optimum. This also we can write as T optimum would be equal to minus delta H divided by R ln E A minus delta H by K naught E A into C B by C A. So, this is the expression for optimum temperature in a plug flow reactor. So, the equations is T optimum is equal to minus delta H by R ln E A minus delta H by K naught E A C B by C A. So, this is the expression. So, this expression gives the optimum temperature trajectories in terms of the concentration or the extent of reaction or whatever reaction progression variable we choose. So, this will give the optimum temperature, how it will progress in a plug flow reactor. Initially, if we look into for the exothermic reaction as we discussed for the batch reactor as well, this will give an optimum temperature which is negative, because delta H is negative for exothermic reaction. So, that is not physically meaningful results. The optimum temperature becomes infinite when the quantity inside the algorithm, inside the logarithm in the denominator is equal to 1. That means, when this term becomes 1, then the optimum temperatures become infinite. So, that means the term C B by C A is equal to K naught E A by E A minus delta H. So, when this equal to this, then these terms become unity inside the logarithm. So, C B by C A is equal to K naught EA divided by EA minus delta H. For conversion smaller than this critical value, the optimum temperature is as high as possible. So, if the conversion is smaller compared to this critical value, where it will become the term inside the logarithm become 1, till that point the optimum temperature we should keep as high as possible. As the reaction proceeds past this point, the optimum temperature decreases. So, initially we should keep as high as temperature possible, then decrease the temperature as the conversion will increase. So, the optimum temperature trajectories for a PFR with a single reversible reaction to run the reactor at highest temperature possible until the conversion reaches a point where the optimum temperature obtained from the above equation is Tmax. After that point, the optimal temperature decreases along the length of the reactor with optimum value obtained from the T optimum equations. So, we have derived the equations for to obtain the optimum temperature, which gives the optimum temperature progression. So, initially we need to keep the temperature at the inlet of the reactor is as high as possible, because at that point the conversion is low, and so we need to have as fast as the reactions possible. So, the reactions complete with a smaller time, and then we decrease the temperature at the reactant goes through the reactor length as it passes through the length of the reactor. So, then optimum temperature from time to time we can obtain from the optimum temperature profile equation. So, now let us consider ideal mixed flow reactor overall mass balance. As we have discussed earlier, that for the mixed flow reactor, because of the homogeneous mixing of the content of the reactor, the concentration is uniform everywhere inside the reactor. So, there is no special distribution of the concentration inside the reactor. So, the steady state mass balance equation for CSTR is an algebraic equation. So, if we consider CSTR, the mass flow rate into the reactor is rho naught Q naught, mass flow rate out is rho Q, and rate of production of mass within reactor is equal to 0. So, the rate of accumulation would be equal to d rho v dt, and all these terms are having the usual meaning and significance. So, the overall mass balance equation should be d rho v dt would be equal to rho naught Q naught minus rho Q. Now, if the reactor volume is constant, for constant volume we can take out V outside. So, we can write V d rho dt is equal to rho naught q naught minus rho q, that is for V is equal to constant. Now, if we assume the density rho naught, that is the density of the fluid is same as the density inside the reactor at any time, then we can simply write Q is equal to. So, this is the overall mass balance relation. Now, if we consider mole balance, species mole balance, we can, for a particular species K, we can write the species mole balance as flow rate of species K into the reactor is equal to Q naught C K naught. Flow rate of species K out of the reactor is equal to Q C K. Now, the production within the reactor that is due to the chemical reaction, it would be V, and if multiple reactions is happening, I is equal to 1 to m alpha I k R I, and the rate of accumulation within the reactor that would be d of V C K dt, which is V d C K dt for V is equal to constant. So, now if we write the overall balance equation, we can write V d C K dt would be equal to Q naught C K naught minus Q C K plus V summation over I is equal to 1 to m alpha I k R I. If the density inside the reactor is same as that of the outside that of the feed, then we can define the residence time tau is equal to V by Q naught, which is equal to V by Q. So, then this equation we can write as d C K dt would be equal to C K naught minus C K by tau plus summation over I is equal to 1 to m alpha I k R I. So, this is the species mole balance equation under the conditions of the constant density. Now, we can write the energy balance equation for flow rate of enthalpy into the liquid into the reactor. So, flow rate of enthalpy into the reactor would be Q naught rho naught into H naught cap. Flow rate of enthalpy out of the reactor would be Q rho H cap, and rate of production of enthalpy within the reactor would be 0. Rate of accumulation of enthalpy within the reactor would be equal to d rho v h cap dt. So, if we write the balance equation from here, it would be d rho v h cap dt would be equal to q naught rho naught h naught cap minus q rho h cap. For constant volume system, this would be V into d rho h cap dt would be equal to q naught rho naught h naught cap minus q rho h cap. Now, if there is no heat transfer through the wall, but the reactant which is coming inside the reactor and the enthalpy is going out with the product which is going out from the reactor. So, we can write similarly in case of the batch reactor we have done, we can write d rho h cap dt is equal to rho Cp cap dt by dt plus summation over k is equal to 1 to n for n number of species h f k d c k dt. So, we can get the enthalpy temperature relationship. Now, we can write under steady state conditions, we can write this relation would be q naught rho naught h naught cap would be equal to q naught into rho naught Cp naught cap T minus T reference plus summation over k is equal to 1 to n h f k C k naught. Similarly, we can write q rho h cap would be equal to q into rho Cp cap T minus T reference plus summation over k is equal to 1 to n h f k C k. Now, if we substitute these three terms in the energy balance equation, we can write V is equal to, so V into rho Cp cap dt by dt plus summation over k is equal to 1 to n hfk dck dt. So, this is nothing but V into d rho h cap dt. So, this term can be written as this. Then if we substitute the other two terms, this would be equal to q naught rho naught Cp naught cap T minus T reference plus summation over k is equal to 1 to n Ck naught Hfk minus q rho Cp cap T minus T reference plus summation over k is equal to 1 to n Ck Hfk. Now, if we assume constant volume, constant density and constant heat capacity. So, assuming constant volume, constant density, heat capacity, etc., we can write rho Cp cap dt by dt would plus summation over k is equal to 1 to n Hfk dck dt would be equal to rho naught Cp cap T naught minus T divided by tau plus summation over k is equal to 1 to n Ck naught minus Ck into Hfk divided by tau. Now, if we substitute the derivative in this expression, that is dck dt we have derived earlier. If we substitute that, that is basically Ck naught minus Ck by tau plus summation over I is equal to 1 to m alpha I k r I. If you substitute in the earlier equations, we would obtain rho Cp cap dt dt plus summation over k is equal to 1 to n Hfk. Now, if we substitute dck dt here, it would be Ck naught minus Ck by tau plus summation over I is equal to 1 to m alpha I k R I would be equal to rho naught C p cap T naught minus T divided by tau plus summation over I k is equal to 1 to n C k naught minus C k into H f k divided by tau. Now, from the both sides the term summation over k is equal to 1 to n C k naught minus C k into H f k by tau will cancel from both sides, and using the definition of the heat of reaction, this relations will reduce to rho C p cap dt dt would be equal to rho naught C p naught cap T naught minus T divided by tau plus summation over I is equal to 1 to m minus delta H I R I. So, this is the energy balance equation for the CSTR. Now, if the reactor is not adiabatic, there would be heat flux through the wall. So, if there is heat flux through the wall, say QH, in that case this should be added into the energy balance equation and we would obtain rho C p cap dt dt is equal to rho naught C p cap T minus T naught minus T divided by tau plus summation over I is equal to 1 to m minus delta H I R I, and then for QH heat flux it should be QH by V. So, this is for non-adiabatic systems where there is a heat flux through the wall. So, thank you very much for attending this lecture, and we will continue our discussion on the reactor design and particularly the energy balance equation for the CSTR, where we would see so many interesting phenomena happens when we have a single reaction. We will discuss those phenomena for the basically that is called the steady state multiplicity of the CSTR or continuous mixed flow reactor. Thank you.